Let's talk about oxygen content. And I'm going to actually spell it out two ways. One is kind of the full word, oxygen content, or the full term. And then I'm also going to give you kind of the shorthand, what you might see. Sometimes it's written this way, CaO2. And the C is the content. The little a is arterial, and the O2 is oxygen. So what it means exactly, and the way we kind of think of it, is how much oxygen is there? How much is there? And we measure it in milliliters per 100 milliliters of blood. So per 100 ml, and sometimes you might see deciliter instead of milliliter. Let me just quickly jot that down. That equals 1 deciliter per 100 milliliters of blood. So this is the definition. Now let's use this definition right away. Let's see if you can think through this idea. So let's imagine I go down and I decide to get 1 pint of blood taken from my left arm. Let's, instead of pint, let me write pint. And this is my left arm. And let's say I'm in a huge rush this day. So I decide that I also want to get another needle stuck in my right arm. And they also draw blood out of my right arm, kind of at the same moment, the same time. So the same kind of blood, same hemoglobin concentration, and same amount of oxygen in my lungs when I was getting the blood drawn. Except for some reason, maybe this needle, this second one, was larger, and they were able to get more blood out, 2 pints. Now some smart, wise guy walks by and says, hey, which side, your left or your right, were you able to get higher oxygen content from? Now, just looking at the picture, you might be tempted to say, well, oxygen content sounds like the right side is the winner. But actually, this is kind of a trick question, right? Because it's per 100 milliliters. So you got to remember, it's a certain volume that we're thinking about. And in this case, since we know that the blood was drawn at the same moment from my 2 arms, and I have no reason to believe that the left versus the right had a higher oxygen saturation, I would say actually probably the 2 had the same oxygen content. That would be my guess based on this setup. So that's one important thing to remember, that it's per 100 ml. So let's just keep that in mind. And now let me actually just jot down for you the exact equation, kind of the formula. If you wanted to mathematically calculate oxygen content, how would that look? Well, CaO2 is quicker to write, so let me just jot that down. And the units on this are milliliters of oxygen per, I said, 100 milliliters of blood. So these are the units here. And this is going to equal, to kind of figure this out, I need to know the hemoglobin concentration. And there it's the grams of hemoglobin per 100 milliliters of blood. And then I have to multiply this by a constant. And the constant is 1.34. And what that number is it's telling me the milliliters of oxygen that I can expect to bind for each gram of hemoglobin. So that's actually quite a nice little number to have handy, because now you can see that the units are about to cancel, right? This will cancel with this, right? And I end up with the correct units. But there's one more thing I have to add in here, which is the oxygen saturation. Remember, this is O2 saturation. O2 saturation. And if I know the O2 saturation, remember there's this nice little curve. This is O2 saturation. And if I'm looking at just the arterial side, I could write S little a O2. And I could compare it to the partial pressure in the arterial side of oxygen. And remember, we have these little S-shaped curves, right? These S-shaped curves. And all I want to kind of point out is that for any increase in my PaO2, in the partial pressure of oxygen, I'm going to have an increase in the O2 saturation. So there's an actual relationship there, and we usually measure this in percentage, right? Percentage of oxygen that is bound to hemoglobin. And so this is the same thing here, as a certain percentage. So this whole top part of the formula then, this whole bit in my brackets, really is telling me about hemoglobin bound to oxygen. Now remember, that's not the only way that oxygen actually travels in the blood. Let me write out the second way that oxygen likes to get around. And the second way is when it dissolves in the blood. So this is all going to be plus, and the second part of the equation is the partial pressure of oxygen, and this is measured in millimeters of mercury. So that's the unit. And this is times, now this is another constant, 0.003, and then keep track of the units here because we have to end up with these units, right? So you know everything has to cancel out to end up with that. So I have milliliters of oxygen on top, and I'm going to want to cancel my millimeters of mercury. So take that times 100 milliliters of blood. So these are the units on the bottom, and they end up kind of the same as we just worked through. We've got this crosses out with that, and my units are going to end up perfect, right? And this bottom bit that I'm going to put in purple brackets, this bit tells me about dissolved oxygen. So I have my oxygen bound to hemoglobin, and I have my dissolved oxygen. These are the two parts of my formula. So let me actually just quickly, before I move on, circle in blue then the important parts that I want you to kind of keep your eyeballs on. There's the total O2 content, hemoglobin, oxygen saturation, and partial pressure of oxygen. And remember, this guy influences this guy, and we saw that on the O2 curve that I just drew. Let me just bring it up again so I can remind you what I'm talking about. In this graph, you can see how the two are related, right? So there's a very nice relationship between the two. So this is my formula for calculating the total oxygen content. So let's actually use this formula. Let's think through this. And when I think through it, I always kind of go through all of my 4 variables. Let me just jot them down here so we keep track of them. Let's do PaO2, SaO2, and then hemoglobin, and the total oxygen content. These are my 4 variables. Now let's do a little problem together. Let me make a little bit of space. And let's say I have two little containers. And the first container, this first one, is full of blood. Here's a B for blood. And here's a second container full of plasma. Remember, plasma is a part of the blood, but it's not all of the blood. Plasma specifically does not have any red blood cells or any hemoglobin. So let me just write that down. No hemoglobin in the plasma side, just to kind of make sure we don't lose track of that fact. Now plasma is kind of yellow colored, so let me just kind of make it yellow colored here. Make sure we clearly see that that's plasma, and blood I'm going to keep as a red color. So now we have our 2 containers full of plasma and blood. So now let's say I decide to increase the partial pressure of oxygen in the air. So it's going to diffuse in here, and it's going to diffuse in here. So I increase the partial pressure of oxygen in the air, and it's going to diffuse into those 2 liquids. It's going to dissolve into those liquids. So my question is, as we go through one by one each of these 4 variables, I want you to think through if they go up, if they go down, or if they stay the same. So let's start with the first one, PaO2. Well, if the oxygen is going to diffuse into those liquids, then I would say the partial pressure of oxygen in the liquid would go up. Now it's a little bit confusing to use the words PaO2 in this case, or even down here, CaO2 or SaO2, because we're not really talking about arterial blood here. We're just talking about blood. And we're not talking about arterial plasma. We're just talking about plasma, because there's no artery connected to these 2 tanks of fluid. But the concept is the same. So the partial pressure of oxygen is going to go up in the blood, and it's going to go up in the plasma because it just dissolves into those liquids. Now what about saturation of oxygen? Well, O2 saturation goes up in the blood. Remember, there's a relationship, we said, between PaO2 and oxygen saturation. So it's going to cause the SaO2 to go up here. Whereas on the plasma side, there is no hemoglobin. So of course there's going to be no change here. I would say not applicable. not applicable, because there is no hemoglobin, so how can you have an oxygen saturation curve for hemoglobin? Now what about the third variable, hemoglobin concentration? Remember, that was grams per 100 milliliters of blood. Well, I'm not talking about adding or subtracting hemoglobin, so there should be no change here, right? I'll write no change. And on the other side, on the plasma side, again, there is no hemoglobin, so it's not going to affect that at all. It's not really applicable. Plasma, again, does not have hemoglobin. So in terms of the total oxygen content, or the CaO2, would I expect it to go up in the blood? Definitely, right? It's definitely going to go up because the dissolved part of the equation goes up, but even the hemoglobin bound to oxygen part of the equation goes up because we said the SaO2 went up. That's an interesting point, right? On the other side, on the plasma side, it also increases, but only a little bit, because here you only have the contribution from the PaO2. You have no contribution from any of the oxygen bound to hemoglobin because, again, there is no hemoglobin. So this problem kind of illustrates some of the ideas, specifically around trying to tie in an increase in the partial pressure of oxygen to how that could affect the saturation of oxygen.